Chapter 5, Part 4, Hydration of Alkenes. The first reaction we're going to look at is acid-catalyzed hydration. These are reactions with any combination of water and acid. And what you'll see in the examples is that water and acid can show up as reagents in several different ways. You might see it as literally water and H+. It might be hydronium, H3O+, because that's what forms when you mix water with acid. It might be something like water and sulfuric acid or 0.1 molar sulfuric acid. Those are all ways of saying that I have both water and acid present. In an acid-catalyzed hydration, you have an alkene reacting with acid and water to form an alcohol. Now it's worth adding here that this is also a Markovnikov addition, so it's not only an alcohol that's going to form, it's going to be the most substituted alcohol. Okay. So the most substituted alcohol will form because we're going to go through the most substituted carbocation. I'm going to erase that. It looked like a serial killer wrote that. So in this mechanism, it's going to start the same way that our hydrohalogenations started. We have our acid, we have an alkene. The first thing that's going to happen is the alkene gets protonated by using the electrons, the pi electrons of the alkene, to attack the proton. We form a carbocation. So remember, since this is a Markovnikov addition, we're going to put the proton on the least substituted carbon and the carbocation on the most substituted carbon. From here, we're not actually going to form our nucleophile through our protonation this time. What you'll see is that if you have like hydronium as your source, then you kind of do, because you're going to have water as the byproduct of that protonation, deprotonation. But if you're reacting with sulfuric acid, hydrogen sulfate is not capable of acting as a nucleophile. And when we get into chapter 7 and we really talk about nucleophiles and what makes a good nucleophile, you'll understand why. But the main issue is that even though it is a weak base, it's quite large and bulky, and so it's what we call a non-nucleophilic acid. So by using it to protonate something, you do not also generate a nucleophile. So the nucleophile in this reaction is actually water. And so this is going to give us something that we haven't seen before, which is that when the water attacks, we end up creating a charged species. So water forms a bond with that carbocation carbon. This carbon is going to be satisfied by the use of these electrons here. The oxygen will still have one lone pair. Now this oxygen is going to have a formal charge of +1. And remember that hydrogen that we added is still here. I'm just not drawing it because it's implied. Now, we don't want to leave a positive charge on the oxygen for a couple different reasons. One, because our products in an organic reaction are typically not charged. And two, because oxygen is an electronegative atom, it doesn't really want to exist with a positive charge. So what's going to happen is it's actually going to get deprotonated by another molecule of water, or it could actually be deprotonated by another alkene, because in our mechanism we've shown one alkene reacting with one proton, but that doesn't mean that all the other alkenes aren't going to go through this reaction. And this is an acid catalyzed hydration, which means there's not a lot of the acid going around. So every time that we need to get rid of a proton, it's just kind of getting tossed about between different compounds. And so anytime you have a catalyst, you're going to use the catalyst, but then you have to spit it back out so that it can be used again by another equivalent of your starting material. So water is going to react with this or another alkene, and this gives us our product, the most substituted alcohol. And then we also have H3O+. Now you might be wondering, why am I able to form hydronium when I just said that having a positive charge on oxygen is not good? Two reasons. One, it's not going to last because we do have an alkene that needs to react with it. But also, in the reagents, I gave you water and H+. Those are not actually going to exist separately. What you really have here is hydronium. And since we used one up when we reacted, we're allowed to make another. That's Le Chatelier's principle. But what we can't make is this, which never existed before. So we have to deprotonate it and create something that we used up. So this is our major organic product. So here are two practice problems for the acid catalyzed hydration. The first one is just a basic Markovnikov reaction. You're expected to make the product that would form as the major product using Markovnikov's rule. In the second one, I'm going to go ahead and give you a heads up. This is actually prompting you to do a carbocation rearrangement. So once you draw that first carbocation that you would form, ask yourself, can I make a better one? The answer is going to be yes. And then go ahead and do the rearrangement so that you end up with a more stable carbocation. Now, if you feel comfortable, go ahead and pause. If you don't feel comfortable yet, that's okay. Let's work the first one together, and then maybe you can try the second one on your own. So in these reagents, I gave you water and sulfuric acid. It's fine by me if, when you're drawing out the mechanism, if instead of sulfuric acid, you just want to write H+. All I want to see is that you understand that these electrons are going to attack this proton. So that gives us our cyclopentane. We have that carbon that's still sticking off of there. We have to decide if we're going to put the proton on the most substituted carbon or the least. Markovnikov's rule tells us that we need to put the proton on the least substituted carbon and form the more substituted carbocation. So at this point, since you formed a carbocation, you should ask yourself, can I do better? This is a tertiary carbocation, so no, you cannot do better. At this point, the water is going to attack the carbocation, which gives us this intermediate. And then we are going to deprotonate this to get our product. Now, ideally, at some point, you would get comfortable enough with these reactions that once you've kind of thought through this first step, you can skip ahead to get to the product. So you don't have to draw all of these steps out. So if I were looking at this, I would kind of mentally go through this carbocation and assure myself that I'm not going to do a rearrangement. And then I would just go ahead and draw my structure without the alkene and know, okay, I'm going to put the hydrogen here, and I know that this forms an alcohol, so I'm going to put the alcohol here. That would allow you to get through the problem a little more quickly for the sake of a quiz or an exam. When you're doing your homework, it doesn't really matter how long it takes you. Okay, so the next one, I want to talk through kind of how to do this a little more quickly. I know I just did that up above, but this time I'm going to do it without drawing out the mechanism. You're welcome to draw it out on your paper if you would like. So if I were doing this really quick, trying to answer on a quiz or an exam, instead of drawing out this whole process here, I would go ahead and draw out that carbocation that I know is going to form and just do a little double check for myself that I understand, whether or not I've made the best carbocation. So my hydrogen is going to be here and my carbocation is here. This is secondary, so I should ask myself, can I do better? And in this case, you can. Next door is a tertiary carbon, which means it has a hydrogen atom that could very, very easily do a hydride shift. So this gives us a new, better carbocation. So I'm still going to have my two carbons here, but my carbocation now lives here. So now that I have this, I'm able to draw my product straight from here because I know that this chemistry forms an alcohol. So I'm going to draw out all my carbons and plop my alcohol Oops, sorry, that kind of looks like I was bonding into the middle of the bond. Plot my alcohol right here because I know that's where it goes. So this is my product for this question. If you're not 100% sure about that, go ahead and draw out the full mechanism. But the mechanism looks exactly the way all this did, especially since it ends up being at that joint between a ring and the ethyl group. It's going to look almost identical. The difference being this is a cyclopentane, this is a cyclohexane. This was a methyl group, this is an ethyl. So it's really not very different. The only difference in this problem is that I had the alkene removed from the ring by 1 carbon, which allowed us to have this carbocation rearrangement. Okay, on this last page, this is one of the rare times that I give you a reaction and I say, just go ahead and memorize it. We're not really going to talk about the mechanism here. Your textbook does show it, and my handwritten notes show it, but this is one of those ones where you want to memorize these reagents together because they do one very predictable thing every single time. This is an anti-Markovnikov hydration. So if Markovnikov means we make the most substituted whatever we're making, this is going to make the least substituted alcohol. And furthermore, this mechanism does not have a carbocation intermediate, which is why it does not follow Markovnikov rules. I don't know why it gets mad when I just write words. But mechanisms, it's perfectly happy. No. Okay, no carbocation. I would just write that. So for this reaction, it's very, very simple. All I want you to do when you see these reagents, which actually let's talk about those real fast before we just move on. This is the borane THF complex. THF is a cyclic ether. It looks like this. And it's going to have a Lewis acid Lewis base complex with the borane. You don't need to know that. You don't need to draw it. It has nothing to do with what the structure of the product looks like. And then it's going to react with sodium hydroxide and hydrogen peroxide. And what this is going to do is replace the borane that gets added to the alkene. One other important thing about these reagents is that it is listed as step 1, step 2. And even though we're not learning the mechanism, I do want you to start getting used to interpreting reagents correctly. So what this means is that the alkene would be reacted with the borane THF complex. And after the reaction was completed, it would then be isolated. It would go through a whole workup process potentially, and then the sodium hydroxide and peroxide would be added. So these things are not added at the same time, they're added sequentially, potentially even after an intermediate product is isolated. I've never actually done this reaction myself, so I'm not sure if you do have to isolate the intermediate product, but it's possible that that would be a thing. So anyway, when you see step 1, step 2, that means that this chemistry happens separately. So in this reaction, all I need you to do is draw out the carbon skeleton that you have over here, but omit the alkene. And then on the least substituted carbon of the alkene, so in this case it's going to be this one, not this one, draw a hydroxyl group. This is where your alcohol ends up. So we are just making the least substituted carbon. We choose the least substituted carbon of the alkene. There's no rearrangement again, so you don't have to worry about the alcohol like ending up over here or something. It's going to be on one of the carbons of the alkene, specifically the least substituted. So I deliberately used these reagents because we've already seen both of these carbon skeletons go through Markovnikov chemistry, either with hydrohalogenation or with hydration. So you have something that you can directly compare to. Now, one thing I do want to point out, and I should have been pointing this out all along, is that once we get to this place where we are adding on covalent bonds to reactions, students do start to lose and gain carbons. So that's one of the reasons that I spent some time talking about addition and how it's a 1 + 1 = 2 scenario. So our starting material here has 6 carbons in this ring and 2 carbons here. So this is an 8 carbon starting material. So there should still be 8 carbons over here. And if you've lost one, you've made a mistake. A common thing that I see with students, especially with this type of chemistry, and they're not doing a mechanism or anything, is they draw the carbon skeleton and then they put the OH group here. So what they've done is they've actually lost this carbon. This is a really, really common thing, and students lose a lot of points for just simply not counting. So when you're done with the reaction, I would get in the habit of going, okay, this is 6, this is 8, 6, 8. Just a quick circling of your carbons can save you a lot of pain. If I were doing that for this one, I would say I have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. Just make sure that those carbons from the product side, or sorry, reactant side, makes it into the product side. Again, it'll save you so much trouble. And it can also save you a lot of frustration on Achieve. If you feel like you're doing the right chemistry and you're looking at your product and you're going, I drew the least substituted alcohol, you're probably just missing a carbon, and that happens all the time.